will present some results of ray tracing variation due to varying electron density profiles, which were obtained using different ray tracing methods. It's based on a work of a young scientist of our lab, Mariano Fajri. I will begin with some general concepts which have already been presented by Kate Soddy earlier this morning. So sorry for the repetition of some parts. Ray tracing is a numerical calculation method employed to determine the path of electromagnetic waves or ray paths in a medium, and is carried out by defining first some input parameters like the position of the transmitter and the conditions of the medium, which in our case is the ionosphere, and that will serve to estimate the refractive index. Then we have the ray tracing algorithm, that is the model code or equation to estimate the ray path. And finally, we obtain an output, which can be ray path, ground range, and so on. Ray tracing in the ionosphere is a powerful and useful tool in many modern applications, like radios on radars and telecommunications. And it depends critically on a realistic ionospheric modeling. In fact, a key problem in ray tracing is the refractive index, the ionosphere. And as can be seen from its equation, and as Kate Soddy also explained this morning, it depends on the ionosphere electron density, the magnetic field through the gyro frequency, and the neutral thermosphere through the collision frequency. As an example of ray tracing tools, I will mention IONORT, that is a software tool developed by Azzaroni, Bianchi, and Settimi in the Istituto Nazionale di Geofisica e Volcanologia. It performs three-dimensional ray tracing and also homing simulation, considering the magneto-ionic formula of the refractive index. It has a graphical interface and is a highly versatile and user-friendly application that has proven to be very accurate under real ionospheric conditions. Another example is the PowerLab, which has been considered in the previous talk. That is a tool developed by Manuel Cervera from the Defense Science and Technology Group in Australia. It provides a variety of ray tracing engines, from two-dimensional ray tracing to full three-dimensional magneto-ionic ray tracing. It is also highly versatile and user-friendly, and is very accurate under real ionospheric conditions, and also considering perturbations, for example. And this is the ray tracing tool developed by Mariano Fajri at our institute, which we call it LabTLRT. It is based on the numerical ray tracing by Jones and Stephenson, which is a technique that has been widely used. It has an improved interpolation method, which is more immune to overshoot problem between points, and it has also the homing simulation. I will show some results now using three options of ray tracing. The analytical ray tracing, considering the ionosphere as a quasi-parabolic layer, a simple Snell's law in a layered ionosphere, considering a Chapman layer, and the LabTLRT, considering a real ionosphere using the International Reference Ionosphere Model. The differences reside, in addition to the algorithm, of course, also in accuracy and computational runtime. I will present a comparative analysis between ray tracing outputs by varying ionospheric conditions now. The ionosphere, as you all know, is a highly variable medium. However, mean climatological conditions are useful in order to determine a base level for the design and operation of systems using high-frequency waves. Important variables that determine these conditions are the maximum electron density, the peak height, and the shape of the density profile. So we will see how variations in these three parameters of the ionosphere affect one ray tracing output, that is the ground range. This is the first option, where approximations must be made in order to be able to integrate analytically the ray tracing, and we obtain an analytical expression for fully analytical expression for the ground range. The refractive index has the simple form, and assuming this the red curve as the electron density. Of course, it is far from the real ionosphere, but we use it to obtain this analytical solution. This is the second option, which consists in the Snell's law applied to a layered ionosphere. It's a very simple model also. I will not go into details, but just say that it is very easy and fast to implement. You just have to set a height path dividing the ionosphere into uniform slabs, and then Snell's law is applied to each boundary, and there are no limitations for the density profile, unlike the previous method I showed you. In this case, which I mentioned before, it's a ray tracing based on Hamilton's equation given by Hasse-Roe in spherical coordinates. Here is the Hamiltonian, and it's the refractive index, as we have previously mentioned, and a numerical integration of these equations is made at each point. The main inputs here are the electron density profile, the Earth magnetic field, which can be turned on and off, and the collision frequency, which has many options in the mode. Key parameter for the ionosphere is the location, year, month, and local time, since this layer varies with all these factors. Now let's go to some results with the first two ray tracing, which I will call low performance models, but which are simple and fast and can be useful for some purposes. We begin by considering different profiles, but with the same density peak and height peak. That is the same F/2 and HMF2 values. We have in the middle a Chapman profile, that is the black curve, with a given scale height of 70 kilometers, which will be the reference profile, and one which has a scale height 10% bigger, and another one which is 10% smaller, and we also have the quasi-parabolic profile, which is the red curve, also with the same F/2 and HMF2 values. Considering a signal frequency, an example of 12 megahertz and an elevation angle of 8 degrees, to the left, we have the ground range considering a Chapman layer in terms of F/2 and different values of the peak heights. As expected, the higher F/2, the shorter the ground range, and the higher HMF2, the longer the ground range. The figure in the middle shows the percentage variation of the ground range when the scale height is decreased to 60 kilometers. It can be seen that the ground range in all cases increased, and the figure in the right panel shows the percentage variation of the ground range when the scale height is increased to 80 kilometers, and in this case, the ground range in all the cases decreased. Here at the bottom, to see more clear this variation in terms of F/2 and HMF2, we have, for example, here I have varied the HMF2, keeping fixed the F/2 in 9 megahertz. And here I keep fixed the HMF2 in 280 kilometers and vary F/2. We see clearly that when the shape of the profile changes by increasing its ionization, the ground range decreases and vice versa. Even though it is not linear, we can also mention that increasing ionization has stronger effect than decreasing it by the same amount in percent. In our example, for example, a 10% decrease induces a ground range increase of around 10%, while a 10% increase can induce a decrease of around 20%. And for a fixed F/2, this effect is stronger for lower peak heights, and for a fixed peak height, this effect is stronger for higher F/2. Here we made the same analysis, but considering the quasi-parabolic layer, which for the same F/2 and HMF2 as the Chapman layer mentioned here, it contains more ionization as we have seen in the plot of the profile. So the variation is similar as the case where the scale height is increased. So the ground range always decreases. We have some particular estimations where we can see more clearly. I will go fast through this. And now we will see some results with the LabTel ray tracing, most of which have been already published in 2019 in a paper which I mentioned here. And Okay, the ray tracing code uses an electron density profile, in this case generated by the IRI model. And here we consider a quiet day around the equinox and solar activity maximum conditions. We consider eastward propagation with 10-degree elevation and a 12.5 megahertz signal frequency. The options for ED are URSI for FOF2 and M3000 for HMF2 model. We consider also the IGRF magnetic model with 10 tone. That's why we obtain different results for eastward and for northward propagation. We will see just eastward here. Here we have the ground range, which reproduces mainly the spatial pattern of the peak height. In the lower panel, we have to the left the difference in HMF2 when we change the HMF2 model in IRI from M3000 model to AMTB. And to the right, we have the consequent variation in the ground range, which can reach 80 kilometers, that gives more than 30%. In our paper, we also analyzed a northward propagation. The ionosphere is more similar to free space in this case when the field is stronger, and this condition is also favored when a signal is traveling along the field line. Since the present field is almost at an axial dipole, and northward propagation should attain longer ground range, and that's what we obtain. However, the ground range differences in these cases do not exceed 50 kilometers, and they are much smaller than those due to variations in the electron density profile. Okay, this is just to show the difference between the three ray tracing models here presented. The LabTel RT, here is the Snell's law applied with the Chapman layer, and the analytic ray tracing. There are big differences, but of course we have to consider that these two cases are not real ionospheres. So we have a very, very huge variation reaching 100%. Let's move now to the discussion and conclusions. And first of all, analytical ray tracing techniques are much faster than numerical approach, but they have several restrictions, and the ionospheric profile can be very far from the real one. Snell's law applied to a layer ionosphere, as we have shown with the Chapman ionosphere, is an oversimplification, but it should be tested with IRA profiles. We haven't done that yet. Ray paths are very sensitive to the ionosphere electron density profile, and so they are sensitive to the model we use. We have shown here some estimations, but there is a lot more to do and analyze yet. The ionospheric charge density and the Earth's magnetic field affect the refractive index, which in turn restricts the values of the radar or signal frequency and of the elevation angle that can be used, and they in turn again define the ray path, the range, and so on. Regarding the models, all models have a certain degree of abstracting and idealizing in order to be more easily understandable and practically applicable. Our first and second ray tracing tools are lower performance models, especially when compared to LabTel RT, but despite being highly simplified models, interesting and applicable results can still be obtained, especially for sensitivity and comparative analysis like the one we present here. And something I want to mention, since ray tracing is so sensitive to the ionosphere, then probably the geomagnetic field secular variation should be taken into account, especially around the magnetic equator in South America, where the fastest shift is taking place, and also around the magnetic poles. Phil Erickson will tell us more about this later. And we have two effects here. First, the changes in the ionosphere, whose spatial pattern is determined by the magnetic field, especially in the equatorial ionosphere. Here I have drawn some ray paths with no magnetic field, and then increasing the magnetic field, the ionosphere becomes more like free space, so you can attain a longer ground range. And also, we have the cooling and contraction of the ionosphere due to the increasing greenhouse gases concentration, which not only affects the troposphere, but also the upper atmosphere, and is expected to lower the ionosphere, that is lower peak height, and also to decrease the electron density. Here I am showing as an example the results published by Cannon et al. From 2004. Okay, this is all. Thank you.